To get us started, here's a review of the previous lesson. Classify each non-zero element of Z12 as a unit, a zero divisor, neither, or both. Then please do the same in Z12. So if you could pause the video and work on this task, and we'll go over them in a moment. Let's start with the units. Recall that units of a ring refer to elements that have multiplicative inverses. So for Z12, it's the elements of U12, namely 1, 5, 7, and 11. It turns out that each of those four elements is a self-inverse. So for example, 1 times 1 is 1, mod 12, 7 times 7 is 1, mod 12, and likewise for 5 and 11. Now for the integers z, there aren't too many units. In fact, 1 and -1 are the only units, and they are also self-inverses. 1 times 1 is 1, -1 times -1 is also 1. Now let's talk about zero divisors. These are rather strange elements of a ring, non-zero elements that multiply together to 0. So in Z12, we have 2 times 6 equals 0, so 2 and 6 are zero divisors. 3 times 4 is 0, so 3 and 4 are zero divisors. 8 times 9, 72, mod 12 is 0, so 8 and 9 are zero divisors. And then 10 can pair up with 6, because 10 times 6 is 0 mod 12, so 10 is also a zero divisor. So these are the zero divisors of Z12. What about the integers? Well, if you take a pair of non-zero integers and multiply them together, the product is still non-zero. And therefore, the ring of integers does not have any zero divisor. Now, what about elements that are neither a unit nor a zero divisor? Other than 0. 0 happens to be neither a unit or zero divisor, but in Z12, all of the non-zero elements, namely 1 through 11, are accounted for as either a unit or zero divisor, so there is no neither element in Z12 except for 0. What about the integers? Well, 1 and -1 are units, no zero divisors, so all integers besides +1, -1, and 0 are neither a unit nor zero divisors. So almost all integers are neither a unit nor zero divisor. Now what about both? Are there any elements that are both a unit and a zero divisor? Looking at this table, we don't see any in Z12 that are in both of these rows, and we don't see any for the integers either. And this is something that we proved in the previous lesson, that in any ring, an element cannot be both a unit and a zero divisor. So, not surprisingly, in Z12 and Z, both is not possible. Now here's a new definition, but even before we get to it, I'd like to highlight this phrase, commutative ring. Now recall that in any ring, addition must be commutative. A plus B must equal B plus A, and that's built into the definition of a ring. However, multiplication does not have to be commutative in a ring. Now, in Z or Z12, A times B does equal B times A for any pair of elements A and B. But we have seen examples, such as the matrix ring, where multiplication isn't commutative, and that's okay. So when we refer to a commutative ring, we are saying that multiplication in that ring is commutative. And when we say a non-commutative ring, we are saying that multiplication in that ring is not necessarily commutative. And with that, here's a new definition. A commutative ring is called an integral domain if it does not contain any zero divisors. For example, the ring of integers Z is an integral domain. It is a commutative ring because multiplication in Z is commutative, and as we see in the table, Z does not contain any zero divisors. However, Z12 is not an integral domain. It is a commutative ring, but Z12 has a bunch of zero divisors, and therefore it is not an integral domain. Now please pause the video and work on day 27 classwork, and afterwards we'll discuss some of the problems and concepts. Let's discuss the cancellation property in an integral domain. In the ring of integers Z, for instance, which is an integral domain, we have the following. If 3b equals 3c, then we can cancel the 3 from both sides and conclude that b must equal c. Now you might say, well, why not just divide both sides by 3? Well, recall that division is not a valid operation in a ring, and we can't even multiply both sides by 1/3 because 1/3 is not an integer. So there is something to prove here using the fact that Z is an integral domain. But before that, let's take a look at a non-example, Z12, which does have zero divisors, so it's not an integral domain. Here we have 3 times 10, that's 30, mod 12 is 6. 3 times 6, 18, mod 12 is also 6. So we do have a scenario where 3 times b equals 3 times c, where b and c are 10 and 6 respectively. However, 10 certainly doesn't equal 6, and so we have b does not equal c, even though 3b equals 3c. So here's a case in a non-integral domain where the cancellation property fails. Now let's generalize this as a theorem. Let a, b, and c be elements of an integral domain with a not equal to 0. Then the cancellation property states the following. If ab equals ac, then b equals c. So let's proceed as usual and identify the hypothesis, namely AB equals AC, and the conclusion B equals C. So that gives us the very first step of our proof, assuming the hypothesis, and the very last step, thus the conclusion B equals C. So how can we proceed? Well, right now we have the equality AB equals AC. And as we discussed earlier, we can't multiply both sides by A inverse because the multiplicative inverse of A may not exist in this ring. So instead, we can subtract AC from both sides, end up with AB minus AC equal to 0, and then we can factor out the A and end up with A times B minus C is equal to 0. And therefore, we have a pair of elements, namely A and B minus C. So let's treat B minus C as one element that multiply together to be 0. Now, since we're in an integral domain, that means A must equal 0 or B minus C must equal 0, or possibly both of them 0. And that's because if neither of them is 0, that means we would have a pair of non-zero elements, A and B minus C, multiplying together to be 0. That would make them 0 divisors. But we're in an integral domain, so we can't have 0 divisors. And therefore, we must have A equal to 0 or B minus C equal to 0. we're using in this argument what's called the zero product property. And please read chapter 27 for a more careful discussion of the zero product property. But for now, let's move on with our proof. So we've shown that A must equal 0 or B minus C must equal 0. But one of our given conditions is that A does not equal 0. So we must have B minus C equal to 0, and adding C to both sides, we get B equal to C as desired. And that's the end of our proof. Now, let's take it a step further and see where our proof, when applied to Z12, fails. So earlier we saw that in Z12, 3 times 10 equals 3 times 6. Then let's follow as we did in the proof and try to show that 10 equal to 6 in Z12. We know they don't equal to each other, so somewhere along the line, the argument must fail. And so let's see where that occurs. Well, the first step is subtracting 3 times 6 from both sides. So we get 3 times 10 minus 3 times 6 is 0. That's still valid. This is 30 minus 18, which is 12. And in Z12, 12 equal to 0. Factor out the 3, still a valid step. And then using the same color coding, we have 3 times 10 minus 6 is equal to 0. And that's still true in Z12 because this is 3 times 4 equal to 0. And so that's what we have in Z12. But notice now we have a pair of zero divisors. And that's where the argument fails. Because when we were in an integral domain, we were able to say that either 3 is 0 or 4 is 0. But that's certainly false in Z12. And once again, what makes this proof fail is the existence of zero divisors in Z12. And that's why this theorem and proof is only valid in an integral domain where zero divisors do not exist. In the classwork, Elizabeth noticed that the rings Z7 and the real numbers R are almost multiplicative groups. And that's because every non-zero element in each of those rings has a multiplicative inverse. And motivated by that observation, here's a definition. A commutative ring is called a field if every non-zero element is a unit. In other words, if every non-zero element has a multiplicative inverse. And the key here is that in a field, we can always divide or multiply by the multiplicative inverse of A, except when A is 0. Now, examples of a field include Z7 and the real numbers R. And it turns out that both of those fields are also integral domains. And in fact, that's always true. Here's a theorem. If R is a field, then R is an integral domain. So let's think about the proof of this theorem. And as usual, we'll start by identifying the hypothesis and the conclusion. And we'll give a proof outline for this theorem. So we know the first and the last steps. We'll begin by assuming that R is a field, and we'll conclude at the end that R is an integral domain. Now, to show that R is an integral domain, we must show that R doesn't have any zero divisors. And here's a strategy to do that. Let's start with an arbitrary element of this ring that is non-zero. So we'll let alpha be a non-zero element of this ring. And then we have to show that alpha is not a zero divisor. That will tell us that R is an integral domain. So how can we show that alpha is not a zero divisor? Well, we're in a field and every non-zero element is a unit. And therefore, alpha must be a unit. But we saw in the previous lesson that a ring element cannot be both a unit and a zero divisor. So if alpha is already a unit, it can't be a zero divisor because alpha can't be both. And then we've shown that R does not have any zero divisors, and hence it is an integral domain. And so I'll leave it up to you to write down this proof more carefully, but that's the general outline of the proof. One more remark about this theorem is that its converse, namely, if R is an integral domain, then R is a field, that's a false statement. And the ring of integers Z would serve as a counterexample. Recall that Z is an integral domain, but Z is not a field because not every non-zero integer has a multiplicative inverse. In fact, most non-zero integers do not have a multiplicative inverse. So once again, Z is an integral domain, but it is not a field. And therefore, the converse of this theorem is false. Suppose we're trying to solve the equation x squared minus 6x plus 8 equal to 0. One way to do this is by factoring. If we factor the left-hand side, we get x minus 2 times x minus 4 equal to 0. Therefore, x minus 2 is 0, or x minus 4 is 0, which gives us x minus 2 or x minus 4 as possible solutions. Now this is all fine if we're working in an integral domain, such as the ring of integers, but let's say we're working in Z15, which is not an integral domain. Then if we look at this equation, in Z15, x equal to 7 would make this true, because then we get 7 minus 2, which is 5, times 7 minus 4, which is 3. 5 times 3 in Z15 is 0. So x minus 7 would be a valid solution in Z15. Or we can replace this 7 with 14. Then we get 14 minus 2, which is 12, times 14 minus 4, which is 10. 12 times 10 in Z15, 120 mod 15 is 0. And therefore, we get another solution, x equal to 14. So here's a takeaway from this example. Funny things happen when we're not in an integral domain. So when we're in Z15, which is not an integral domain, we could have strange things like having 4 solutions to a quadratic equation. Now let's take this a step further, and we'll solve our quadratic x squared minus 6x plus 8 equal to 0 in Z15 using the quadratic formula. So here's the quadratic formula, just as a reminder. And once again, Z15 is not an integral domain, so we expect something funny to happen. Let's see what that is. So using the quadratic formula, we get x is equal to negative minus 6, that's b, plus or minus the square root of negative 6 squared minus 4 times 1 times 8 all over 2 times 1. So simplifying that, we get negative minus 6 is 6 plus or minus the square root of 36 minus 32, that's 4 all over 2. And so we can go ahead and solve this. This would be 6 plus or minus 2 all over 2. And if we do 6 plus 2 divided by 2, we get 4. 8 divided by 2. Or if we do 6 minus 2, that's 4 divided by 2 is 2. And so we get the initial two solutions that we found by factoring. Now, rather than taking this in its natural path, let's take it in a different direction. So I'll rewrite it as follows. We'll still have the 6 plus or minus square root of, and instead of 4, now we're in Z15, and in Z15, 49 is the same as 4. And so let me just highlight the fact that 4 and 49 are equal in Z15 because their difference is 45, which is a multiple of 15. So then we can rewrite this as 6 plus or minus the square root of 49, which is 7 over 2. But if we do 6 plus 7, we get an odd integer 13. 6 minus 7, negative 1 is also odd. It's difficult to divide by 2. So let's rewrite this 7 as 22 in Z15. And then we'll divide that by 2. So let me just highlight the fact that 7 and 22 are the same in Z15. So then what do we have? Well, we have 6 plus 22 is 28 divided by 2 is 14. Or 6 minus 22 is negative 16 divided by 2 is negative 8. But let's write this in Z15. Negative 8 is the same as 7. And so we found the two extra solutions that we found earlier. So I'll leave it up to you to find out if those four are the only solutions we have in Z15, or perhaps via zero divisors or quadratic formula, we can find more solutions to this equation in Z15. But the key takeaway here should be that funny things happen when we're not in an integral domain. So with that, this is the end of today's lesson, and I will see you next time.